Hi there, my name's Alexander Rowsell, and we're starting today with the first week of the Serial Bus's HackadayU course. We're going to be learning about I2C in this, the first part. We're going to be covering both the hardware and protocol layers of I2C in this first lesson. We're going to go through things quite thoroughly. The prerequisites, as we posted, were some understanding of programming microcontrollers. Experience with Arduino is good, basic understanding of circuit elements, but as long as you have sort of a general idea of how chips work and if you have any experience programming, you should be okay. My email address is there on screen, amrowsell@frozenelectronics.ca. So, welcome to week one. Super excited to be teaching this course. This is going to be a lot of fun. So the goal of this course is to familiarize you with I2C and one wire in two separate parts, which are two very popular serial buses for microcontroller communication. We're going to be starting with I2C at the hardware and protocol level, and next week will be I2C at the software level. We'll be taking a look at software examples in C, C++, with an MSP 430 microcontroller. There is an Easter egg in this presentation, yes. The first person to find it and send it to my email address, which was on the first slide, will get a $10 Tindy gift certificate, which is really cool. This only applies to the first running of this course, which is the week of September 2nd to the 9th. If you're watching this right after it's come out and you're the first one to find the Easter egg and email to me, then you will get that $10 Tindy gift certificate, which is really cool. A big thanks to Tindy for helping support this course. So, a little bit about me. I'm a Canadian hacker. I specialize in designing and prototyping, building, testing, debugging embedded systems. Embedded is what I do, it's what I am good at and what I love doing. I have a lot of years of experience with I2C and one wire. I2C in particular, I've done a lot of work with. I'm a writer and contributor on the side for HackadayU, the Tindy blog, Supply Frame hardware blog, and also other websites over the years. I've done a lot of writing and contributing to various websites. I spend way too much time drooling over expensive logic analyzers. Eventually, I'd like to get that Tektronix MSO, is it the MSO 5 or the 8 series, where you can have 64 logic channels at once in real time. It's just, they're so cool. So, let's jump into it. What is I2C? Well, I2C, or I2C, short for Integrated Circuit Bus, is a specification for an electrical connection which transmits serial data between any integrated circuits. It can be any arbitrary data at all, with any arbitrary length of data, and it's usually between a microprocessor, microcontroller, and various peripherals and sensors. Although that's not a rule, it can be between two microcontrollers, or it could even be in some cases between two different sensors. Data is sent in a packetized format, meaning that each chunk of data is sent in a specific order and with a delineator of the start and the end of the packet, which we'll get into. Where did it come from? This is a really good question. It was developed by Philips, who are now owned by NXP. They started developing it in the late 70s and early 80s, originally called C-Bus, for use in creating simple control system with their family of integrated circuits. It was supposed to be very simple to implement. If you're a chip designer and you want to add a serial bus to your chip, the idea was that it was going to take up less room on an integrated circuit than competing serial buses like UART, or there's many other choices at the time. It was supposed to be very easy and specifically designed for communication between different portions of a circuit. It's not really intended for communications between two different boards or over long distances. It's really ideal for communicating from one part of a circuit board to another or between various chips. By the early 90s, I2C had become quite popular, and there was a lot of other manufacturers that had started creating circuits compatible with the I2C specification. If you wanted to create them, you had to pay a license fee to Philips to use the I2C logo and implement the standard using their official names like SDA and SCL. A lot of companies avoided this by calling it two-wire or TWI. Atmel, in particular, you might know on the Atmega chips, For a long time it was called TWI. That was to avoid paying these licensing fees to Philips. In 2006, Philips, which had then been bought by NXP, made it a semi-open standard. So you no longer require a license fee to be paid to implement I2C on a chip or to use the official names and all the stuff from the specification. You still do require a license fee if you want to reserve an address in the I2C address space. So if you're making a new chip that is unique from other types of chips and you want a whole brand new address for it, you do have to pay a fee for that. And then just an aside here, we won't be covering SM bus much at all, but just so you know that Intel in 1995, they made an addition to the I2C standard called SM bus for use in personal computers. The differences are that it's much more stringent when it comes to timing and keeping things free of interference as much as possible. On a PC motherboard, there can be a lot of high-speed switching going on. You've got, at that time, ISA and PCI. Now you've got PCI Express. You've got Ethernet. There's all sorts of stuff going on. They wanted a simple bus to communicate between the processor and temperature sensors and basic EEPROMs, that sort of thing. But they wanted it to be a bit more stringent so that it could withstand the conditions on a motherboard and be standardized specifically for use on motherboards. But we won't be covering SM bus. It's not that different from I2C. Most chips that support I2C will support SM bus. So we come to the why. Well, we talked about how it's simple to implement, but there are a lot of alternatives to I2C. Now we've got a whole ton of serial buses that are commonly available on microcontrollers. CAN, which is often used in automotive stuff, you get about a megahertz. SPI, which we'll be covering in part 2 of this course, potentially, up to 100 megahertz, so a lot more speed, a lot more data throughput. USB, you can even step up to that, 480 megahertz for USB 2.0. Now we've got USB 3.1 Gen 2 at 10 gigabits per second. So you can stuff a lot of data over a serial bus. UART, which was competitive at the time when it was developed, you can get easily up to 10 megabaud nowadays. One-wire Ethernet, Bluetooth. There's lots of different options, but none of these really at the time, because SPI wasn't really implemented then. None of these address the ease of use and the low cost of implementation, as well as the low external cost. A lot of these, for example, USB, Ethernet, Bluetooth, you often need an external piece of hardware to the microcontroller. For USB and Ethernet, you have what's called a PHY, which is essentially, it contains the drivers and the low-level logic for that serial standard. Those chips add cost to your BOM, and if you're doing short-range communications between chips, it's not worth spending the money on that sort of thing when you can have a very simple PHY integrated into the chip, and all you need externally are a couple of resistors, as we'll see. So what makes I2C a good choice? Well, as I said, the ease of use and cost. It doesn't require external transceivers, and it's integrated into almost all microcontrollers. There's lots of software libraries that are freely available to use, either full software implementations of I2C or libraries specific to the chip that will take advantage of the hardware I2C that's built into it. The only external components that you need are a couple of resistors, less than a cent in your BOM cost, and if you're buying resistors by huge reels of 10,000 at a time, often way less than even that. It's a simple protocol you can learn very quickly by taking a course like this. So let's dive into I2C at the hardware level. There's only 3 things that are actually connected to the bus. We have a controller, a device which is currently in control of the bus. It controls the clock line and therefore controls the speed at which data is sent and received. You have peripherals, a device which cannot control the bus directly. It has to be told to control the bus by the controller. It's typically a sensor, something that only responds to commands but doesn't actually control the bus directly. And then we have that pair of pull-up resistors which keep both of the I2C lines in their high idle state. I just want to go over a very brief aside here. The I2C specification, and in the industry for many, many years, they've been using terms that are now recognized to be problematic. I2C specification uses the term master for controller and slave for peripherals. In this course and on HackadayU.io and many other places, we're just going to use controller and peripheral, partially in response to the fact that they're problematic, but also to demonstrate how easy and seamless the change is and that it's not a big deal. So hopefully no one will be upset by that. If you are, times move on, and these are the terms we're going to be using in this course. So if you need to refer to the specification, just remember which one pertains to which and just replace the words. It's that simple. So the two lines that are key to I2C, as I mentioned, are called SDA and SCL. SCL, serial clock, used to synchronize each bit. Because I2C is a synchronous protocol, it has to have a clock that lines up with each data bit to clock it in. And SDA, serial data, which is driven low or released high to send the actual bits of data that are being communicated back and forth. This is a very quick look at what an average trace looks like from an I2C bus. You don't need to worry about the decoded logic. I just want you to see that the top trace has just a clock line. It's just going up and down, up and down, up and down. And the bottom trace is going up and down, and it represents the actual bits that are being sent. Top trace SCL, bottom trace SDA. How are they built? Now, this is where the prerequisite of having a basic understanding of circuit symbols is good, but we'll go over this in detail. So on the bus, we have the two pull-up resistors. These, whenever nothing is happening on the bus, they return the bus to its state of idle, which is VCC. It could be 3.3 volts, it could be 5 volts, it could be 1.8 volts. It doesn't matter as long as it's agreed upon between the chips, and all the chips will work with that voltage level. Most commonly, you'll see 3.3 and 5 volts. We have a buffer, which is connected to each line internally inside the chip. This is how it samples what's actually happening on the bus. This is how it listens to what's going on. And then we have FETs, which are transistors which can turn on and off. These are called open drain or open collector because they are connected directly to ground and to the line itself. And when you turn them on, they essentially become a short circuit, and because we've got a high resistance to VCC, it pulls it to ground. Now, this is a really key point with I2C. The only thing a device can do is pull the bus to ground. It can't drive the bus high. It relies on the external pull-ups for that. This has some trade-offs, but it makes some things very simple, such as bus arbitration, which we'll get into later. We also have, there's just some boxes to show. On the left-hand side, we have a controller. On the right-hand side, we have a peripheral. You'll notice that the peripheral only has a FET on the data line. It doesn't have a FET on the clock line. That's because, as I mentioned, the controller controls the clock line, and therefore it sort of is in control of how quickly data is sent and when things happen on the bus. There's also equivalent capacitance on the bus. Now, we're going to just touch on this briefly. If you know your Ohm's law and you've dealt with capacitors at all, you'll know that equivalent capacitance on things like serial buses is a bad thing. Capacitors resist change in voltage, but changes in voltage is how we are signaling and communicating, so we don't want capacitance. So things that are important to remember, as I said, the bus can only be pulled to ground. They rely on the external resistors to pull them back up to their idle state. The value of the pull-up resistors can affect the maximum transmission speed, especially in systems that have many devices attached to the bus. Because we can only pull to ground, yeah, as I said, this has some benefits that make bus arbitration and acknowledge sequences much easier. So this is why pull-ups matter. Remember our RC circuit basics. The length of time it takes to charge a capacitor is directly proportional to the size of the resistor times the size of the capacitor in ohms and farads. If we have too much resistance or too much capacitance, it can make the charge time so long that the voltage is unable to get back to the idle state, making communication intermittent or in many cases completely impossible. So let's take a quick look at what this looks like in practice with some exaggerated examples that help illustrate what can go wrong. So we're going to be looking at some circuit simulation software. Don't worry about all the different symbols you see, we'll go over the important ones. So this is our first example where our bus has too much resistance. We've used pull-up resistors of 1 mega ohm, which is a lot of resistance, and the equivalent capacitance on the bus is quite high as well at 1 nanofarad. Over on the left-hand side, we have a voltage source, which is our bus at 5 volts. And over on the right-hand side, we have that FET that we saw inside the devices earlier. And that's going to be turning on and off to simulate the data or clock line being sent. So in this case, with 1 mega ohm of resistance and 1 nanofarad of capacitance, there's the resistor, there's the capacitor, we get this. This is a very typical signature you'll see on an oscilloscope. We call it shark finning because it looks like a shark's fin. We're starting up at 5 volts, but when we turn the transistor on, we get all the way down to 0 volts, but then we only get back up to just over 3 volts. You can see the charge time has that very characteristic curve to it. We want to avoid this because this will make, we'll have to slow down communication, make those pulses further and further apart so the bus has time to return to its idle state. Obviously we don't want that, so the solution is to increase the resistance, decrease the amount of resistance, or decrease the amount of capacitance. Sometimes we can't decrease the amount of capacitance, so the easiest thing to do is to lower the resistor. So this is an example where it's just right. We have our sort of average value of 4.7K, very common pull-up resistor size for I2C. Now we've got our nice clean 5 volts. When we let go of the line, it snaps back up to 5 volts very quickly. We've got nice clean transitions. This will work great. So speaking about speed, we have various speed options on the I2C bus. We've got the standard speed of 100 kilohertz. Later on, there was a 400 kilohertz mode that was introduced called fast mode. Later, a fast mode plus 1 megahertz, high speed mode 3.4 megahertz, and then there's a new addition to the standard called ultra fast mode that runs at 5 megahertz, and it uses a traditional push-pull type of serial bus, so it doesn't use pull-up resistors. It's a completely different thing. It's not very common at all yet, so we won't really be touching on it. Most of the time you're going to see 100 or 400 kilohertz. Most microcontrollers do support fast mode plus and high speed mode, but most chips typically support 400 kilohertz or fast mode plus 1 megahertz as their top speed. I2C is not really the best if you need to move huge amounts of data really fast. It's really meant for communicating small amounts of data to in between various chips on a circuit board. As I said, yeah, it uses a traditional push-pull architecture like SPI, hasn't found mainstream usage yet. So here's a typical I2C bus. We've got a microcontroller that has SDA and SCL lines connected to some pull-up resistors, which are then connected to a bunch of different things on the bus. We've got all sorts of options when it comes to I2C. Temperature sensors, accelerometers, we've got EEPROMs, barometric pressure sensors, so we can connect as many devices as we want in parallel. They're all connected to the same SDA and SCL. And the only limit on this, as we talked about earlier, is the amount of capacitance. Each one of these devices that we add to the bus will increase the amount of capacitance, and eventually we'll hit a limit. You might have to lower the amount of resistance in the pull-up resistors, or you might run into a hard limit, but it's fairly uncommon. Most buses only have a few devices on them and you don't need to worry about it. So, it's time to look at I2C at the protocol level. Timing is everything. Like with any synchronous protocol, everything is timed against a clock. I2C packets are formed from events that happen on the bus, like any packetized serial format. Every packet starts and ends with a specific event. In the case of I2C, these are called start and stop conditions. They're quite simple. How can a peripheral tell a start or stop condition apart from just data? Well, here's the hard and fast rule. The only time the data line, SDA, can change when the clock line is high is during start or stop conditions. So if the clock line is high and the data line transitions, it is either a start or a stop condition. There's no other situation in which that happens. So during regular transmissions, the controller peripheral must wait until the clock line is low before changing the data line. If you're just sending a regular byte of data, you have to make sure the clock line is low before you change the data line. Otherwise, you'll be sending a start or a stop condition. Let's look at what these actually look like. Here's our start condition. It marks the beginning of an I2C transaction. The bus starts idle, so both SDA and SCL are pulled high by the pull-up resistors to 5 volts or whatever it may be. The data line goes low first, followed shortly by the clock line. The reason that it's a start condition again is because we see the data line goes low first. It changes while the clock line is still high. This is what it looks like on the bus. Over at the left-hand side, you can see clock is on top and data is on the bottom. The data line transitions low while the clock line is still high. Then some amount of time later, the clock line goes low, and that signals a start condition. So now we're ready to start sending data. Well, what's a stop condition? It's essentially the inverse. It's a mirror image. It marks the end of an I2C transaction. So it's an exact mirror image. The bus must be active. Both SDA and SCL are in their low state, so 0 volts. The clock goes high first, followed by data afterwards. Of course, the clock has to go high first to signal a stop condition, because the only way we can signal these conditions is by changing the data line while the clock line is high. This is what it looks like on the bus. We start with both lines low, clock line goes high, and then sometime later the data line goes high. This signals a stop condition. Now the bus is free to be used by other controllers if there are any, or sometimes this will signal to the chip to start executing whatever command we just gave it. There's also a variation of the start condition called a repeated start. This is when we send another start condition instead of a stop condition. This leads into bus arbitration. It's a repeated start, and it's when we want to immediately start a new transaction without letting go of the bus and potentially having another chip step in and start communicating. This is really important if, for example, you've just written a value to a chip and it's done something and you want to read the result out because it's time sensitive. You can't wait, however long it's going to take for another chip to do some sort of communication. So you can do a repeated start. It's also commonly used when you finish writing data and now you want to read data back from a peripheral. For example, we might send the register of the data we want to read, then we'd send a repeated start and then read the data out instead of doing a stop condition and then another start condition. This leads us into bus arbitration. This is one of the lesser known parts of I2C, and it's not something you see terribly commonly unless you have more than one controller on a bus. I2C does support this, but it's not something you'll see commonly. Usually you have a single microcontroller and multiple peripherals, but I2C is capable of either. So why can't it just start reading and writing data to a peripheral? Because there might be another controller on the bus. Whenever any communications protocol has more than one controller, they must have a way to talk to each other and decide who gets to talk when, because we can't all talk at the same time or else the bus turns into a mess. Because I2C devices can only pull the bus to ground, arbitration actually becomes automatic. It's something that you don't need to program in to your software because it's taken care of by the hardware. Here's an example. One controller sends a start condition at the exact same time as another controller. It's unlikely, but it might happen. They both then start to send data on the bus. Every time the controller changes the state of the bus, sets it to a 1 or a 0, it then needs to look at the bus and check that it's actually in the state that it was set to. So for example, if you're trying to send a 1, you need to release the bus line, and the pull-up resistors will pull it back up to 5 volts. But if you've done that and you look at the bus and the bus is still low, that must mean another controller is talking. So we need to stop sending data and wait until we see a stop condition. It's non-destructive as well because we haven't stepped on what the other controller is sending. We released the bus, but nothing happened, so it didn't change what the other controller was sending. And the controller that won arbitration doesn't even know what happened. It never even knew another controller was trying to talk, which is one of the great things about I2C bus arbitration. Here's a very simplified diagram. Often bus arbitration would happen on the very first bit or two, but I've sort of extended this out to show what happens. Two controllers are sending data at the same time. One of them goes to send a 1 at the same time the other one is sending a 0. And the losing controller looks and sees, uh-oh, I wanted there to be a 1 here, but there's a 0. That must mean that another controller is talking, so I need to stop sending data and wait until I see a stop condition before talking again. So this leads us into, again, the two roles we can have on the bus. One device is sending data and the other device is listening. These roles can change during the course of a transaction. The controller is not always the one talking. Peripheral is not always the one listening because, of course, we can read data from a peripheral or we can write data to a peripheral. No matter who is talking or listening, though, as we mentioned earlier, the controller is in control of the clock line, therefore the speed of the transaction. And transitioning between them is simply done by letting go of the SDA line. If you want the other side to talk, you tell them, you signal a command, then you let go and you let them take over controlling the SDA line. But during that time, the controller is still sending clock pulses. So now that we've mastered start-stop bus arbitration, we'll look at how it's actually sent. Every bit is accompanied by a clock pulse. A transition from low to high on the clock line indicates that whatever is currently on the data line is the bit that we're trying to send. It's basically saying this bit is valid right now, so read what's on the line, and that's the bit that we're trying to send. After the clock line goes low, the device currently sending the data changes the data line to the state of the next bit. So again, we have to wait until the clock line goes low to change the data line. Otherwise, it would be interpreted as a start or a stop condition. Data is always sent 1 byte at a time, bit by bit, and bytes are always 8 bits long. Now, this doesn't mean that we can't send 16 or 32 or 64-bit values. We just have to always send them in multiples of 8. This is because I2C was developed in the 80s when everything was 8-bit, but because it's an arbitrary length format, we can send however much data we want. So if we actually decode what's going on, every transaction is initiated by the controller sending a start condition. Peripherals can't control the bus unless they're requested to do so. The controller must send an address with every transaction, and that address identifies the exact peripheral it wants to communicate with. If we've got 5 or 6 devices on the bus, we have to have a way to tell them apart, and they have to know which device is being talked to by the controller, or else they're all going to start responding. So that's why we have addresses. And at the end of every byte, they also acknowledge what's just happened. There's what's called the acknowledge bit. It actually looks like a 9th bit being sent, but it's whatever device is currently receiving data. So whoever's listening at the time, they send the acknowledge bit to say, whatever you've just sent me is valid and I understand it. So we'll look at the acknowledge or not acknowledge, as it may be, in a bit more depth. When a controller starts a transaction and sends an address out to one of these devices, the peripheral, if there's a peripheral there that has that address, it will respond to that address with the acknowledge bit. This is done by the controller briefly letting go of the data line. And if you let go of the data line and there was no device there, it would return to its idle state. So if there is a device there, it holds the data line low while the controller sends another clock pulse. And this is how it says, hey, I'm here, I'm acknowledging the address. If it doesn't match any peripheral or the data sent is incorrect, a not acknowledge is sent. This is actually the default state. Because the bus is pulled high by resistors, if no one does anything to send an acknowledge bit, the default is not acknowledge. The natural state is being pulled high. So let's actually look at how this all sort of goes together. We have at the beginning, like we established, we have a start. So we start with a start condition. In this trace, again, the clock line is on top, the data line is on the bottom. Then, while the clock line is low, we set up the first bit. You can see it goes high there. Then the first time that the clock line on the top goes from low to high, that's a clocking in the first bit, which is in this case a 1. Then the peripheral or whoever is talking at this point waits for the clock line to go low, and then it sets the data line low. It might look like that's happening at the same time there on that very first clock pulse, but if you zoom in really close, there's actually a delay between the clock line going low and then the state of the data line changing. And then the rest of the bits are all zeros, including the acknowledge bit at the end there. So each bit is set, as we just pointed out. And then after the falling edge, the next bit is set up, so on. The byte below is hexadecimal 80, or 1 with 7 zeros in binary. Don't worry about the actual decode below, we'll get to that later. But at the end, as we said, we send 8 bits. As you can see, you can count them. There's 8 clock pulses, and then there's that 9th bit. Below it there, you can see in pink, it says ACK. Because the bus remained low during that last clock pulse, that means whatever device was listening to this data acknowledged it and said, yes, this is valid. So let's take a closer look at how addressing happens. That's actually what we just looked at there, was an address being sent. Addresses are 7-bit values. They're unique to each type of device, and Philips and NXP have tried to sort of keep all similar devices using similar addresses. So temperature sensors might have a specific address that they typically use. EEPROMs have a different address. Barometric pressure sensors have a different address. And because they're 7-bit values, that leaves an extra bit on the end to make an 8-bit value. This bit is actually how we determine what's happening, if it's a read or a write. So yeah, we reserve those addresses by paying a fee to NXP. If you were a chip designer creating a new peripheral, you'd have to pay a fee for one of these addresses. As I said, the address is also how the peripheral knows if this upcoming transaction is going to be a read or a write. The 7-bit address is followed by an 8th bit, which is low if the following transaction is a write, or high if it's a read. This is referred to as the read-write bit. Now, because we're adding a bit to the end, effectively what we're doing is we're taking that 7-bit address, we're shifting it to the left by 1 place, and then we're adding that 0 or 1 on the end to tell the peripheral either we're writing data to the peripheral or we're trying to read data from it. So here's some examples. The SHT21 temperature and humidity sensor, which is actually the sensor we'll be using in our examples in part 2, week 2. The address is 40 hexadecimal in the 7-bit. It's sort of native address. But if we actually want to talk to it, we have to shift it to the left by 1. So it becomes an 80 if we want to write to the device, because that last bit is a 0. Or if we want to read something from it, we add a 1 and it becomes 81. So if you sort of know your basic binary and hexadecimal, if you shift everything over to the left by 1, then it changes the value, and we do a logical OR. I won't get into the details. We'll get into that in the software implementation, but we change the last bit to tell it what we want to do. Now, here's a stumbling block, is that a lot of data sheets will use either of these forms. Some companies will always display things as the 7-bit address, and then they'll specify if you need to add the read or write bit. Others will show the write address. Like, for example, the data sheet might show hexadecimal 80 as the address. So you have to read carefully and ask, are they giving me the 8-bit address or the 7-bit address? Most of the time the data sheets make it clear, just don't assume that it's one or the other. So we'll take another look here. That same transaction we looked at earlier, the software, the logic analyzer that I had hooked up to this, the software has actually decoded this for us. So that byte 0 by 80 in hexadecimal is actually a write to address 40. So you can see at the bottom there, it's decoded it to address write 40. The read-write bit is a 0, and then we have an acknowledge at the end. So even though the byte being sent is hexadecimal 80, the logic analyzer is showing us that this is a write to 7-bit address 40. I know it's a little bit confusing to have these 8 and 7-bit addresses floating around, but you get used to it very quickly when you're working with these devices. At the end, we pull the ACK bit low, meaning the device has responded to this address and it's ready for the transaction, which in this case would be a write. So if we take a summary of everything we've looked at so far, the controller starts any transaction with a start condition, and then sends the address with the last bit high or low, depending on whether it's a read or a write. The device either acknowledges it by pulling the data line low during the ACK bit, or if there's no device there, the default state is for the lines to be in the high state, and therefore it would be a not acknowledge, which is one of the nice things about having pull-up resistors and having the idle state being high. If nothing responds, then it's very easy to tell that because the line will be high. The controller will then continue depending on the status of that acknowledge bit. It'll either keep going, or if it got a not acknowledge, it'll handle that error. So let's actually look at some examples for writing and reading data. Only the controller is able to change the state of the clock line, so it's always controlling the timing. This is very key and can be sort of confusing when you're reading data from a peripheral. You need to provide the clock pulses to it. It doesn't control the clock line. So when the controller is the one putting data on the bus, it is simultaneously setting both the clock and data lines. But when the controller is reading data, it just sends out clock pulses, and whatever it sees coming back on the data line is the data that's being sent back from the peripheral. When the controller is writing, the peripheral is the one that's sending an acknowledge, because in that case, the peripheral is the one listening. Whichever device is listening is the one that sends the acknowledge. Of course, that makes sense. Whatever device is listening is the one that needs to say, hey, yes, I heard what you said. And then vice versa. When the controller is reading, it sends acknowledge or not acknowledge bits. So it sends out clock pulses, gets data back. At the end of every byte, the peripheral is expecting the controller to send an acknowledge saying, yes, I want to read more bytes from you, or a not acknowledge saying, I'm either done reading bytes from you or there was something wrong with what you sent. They'll send a NACK when they're finished reading data. Peripherals will send a NACK if there's been some sort of error. So let's look at a practical example. A microcontroller is connected to an EEPROM via an I2C bus, which is what we've been looking at. It wants to read 10 bytes from address 10F4 inside the EEPROM. If you know anything about how memory is organized, it's just a whole bunch of 8-bit bytes in this case. Each one has a unique address. So we want to read whatever 10 bytes start at 10F4. Don't confuse the address inside the EEPROM, like the memory address we want to read from. Don't confuse that with the device address, which is always 7 bits or 8 bits. The EEPROM's I2C device address is 50, which is actually one of the standard addresses for EEPROMs. That's the 7-bit value. So the transaction will take place in 2 parts because we want to read. So if we want to read something, we first have to write to the peripheral to tell it what we want to do. Microcontroller will send a start condition with the write address, which is A0. That's hexadecimal 50 shifted to the left by 1 bit. And then the last bit is set to a 0 because this is a write. And then after it sends that address, the device address of A0, it then sends the memory address that it wants to read from, in this case 10F4. Then it will send a repeated start, because we don't want another controller on the bus potentially butting in right after we've told the memory we want to read from this address. If we were to send a stop, it's possible that another controller might connect to that same device and change what address is being looked at. We want to make sure that doesn't happen, so we send a repeated start, followed by the read address, which is just the right address, but the last bit is a 1. So in this case, it's A1 in hexadecimal. The controller will then send clock pulses, and the EEPROM will send a bit for every clock pulse that the controller generates. At the end of each byte, the controller will send an ACK until the final byte, when it will send a NACK. And in this case, we want to read 10 bytes, so it'll send an acknowledge, and it'll count up until it gets to the 10th byte. Then it'll set a not acknowledge. Let's actually take a look at this in PulseView. So this is actually the software that I used to probe this exact example transaction. I set up a microcontroller and an EEPROM, and I actually did exactly what we just discussed in that last slide. So if we zoom in here, over on the left you can see the bottom trace is data, top trace is clock. We have a start condition. Both lines are high. Data line goes low. Then the clock line goes low. The software has decoded that for us and shows us that's start. Then we send the first byte, which is an address, and it's a write to address 50. So as you can see, it's actually 1010, which is A0, as we determine is the 8-bit address if we're writing, and we get an acknowledge back, because during this 9th clock pulse, right around here, the controller would let go of the bus, and then the peripheral will hold the bus low while this final clock pulse is sent out. Then it will release it again as soon as it sees the falling edge of that clock pulse, and that's when the bus goes high there for a moment. Then the next 2 bytes that we write are the address that we want to read data from inside the EEPROM. So as you can see, 10F4 is what's actually being written. Then, because now we want to switch to reading data, we have to send a repeated start condition. We could, as I said, in theory, we could send a stop condition followed by another start condition, but then we're risking another controller potentially taking control of the bus from us, which is something we want to avoid. So we send another start condition. Again, it's the exact same as the usual start. We start with both lines high. The data line goes low first, then the clock line. Then we're sending an address read from address 50. So again, we have A1 as the address. You can see it actually separates out the read-write bit for us in this software, which is really nice. So this is actually byte A1, but the software has decoded it for us into a read from address 50. We get an acknowledge because we know the EEPROM is at that address. Then we start reading bytes from it. We read the first byte, and then at the end of that byte, during this section now, as soon as the device acknowledges that read address, the controller then lets go of the data line, and now the peripheral is controlling the data line. The controller keeps sending out clock pulses, and that's how the peripheral synchronizes this, but from then on out, the peripheral is controlling the data line. So it sends out the first byte, which in this case happens to be hexadecimal 48. Then at the end, it lets go of the data line, and the controller then sends the acknowledge pulse, because now the controller is the one listening. So it lets go, the controller keeps the data line low through that 9th clock pulse, and that's an acknowledge, and that's us saying we want to read another byte. It keeps doing this 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Then we get to the final byte. This final byte, same thing happens, we read it out, but at the end, the controller just lets the line return to its idle state. It sends another clock pulse, and the device now, it's a not acknowledge. So the device stops sending data, and we're done with this transaction, so we send a stop condition, which again, we start with both lines low, we set the clock line high, then we set the data line high, and that's the stop condition. As you can see, it's been decoded for us. It's decoded it for us there as a P for the stop condition. So that's a full transaction, reading 10 bytes from an EEPROM. When you look at it piece by piece, it's actually quite a simple protocol. As you can see, we write an address. Depending on the type of device, it'll change what we're actually writing to the device, but we write whatever we want. We send a repeated start, or sometimes a stop and then another start, and then we read from that same address, and it sends us whatever data. In this case, it's data from an EEPROM. It could be temperature sensor data, it could be barometric pressure data, it could be anything. And when you have multiple devices on the bus, all you have to do is change what address that you're reading and writing from, and you're talking to a completely different device. Again, I want to point out that the clock pulses here, as you can see, are very regular. If we actually zoom in and we use the cursors to take a measurement from the end of one clock pulse to the end of the next one, you can see we're running at about 100 kilohertz, 102.5 kilohertz. So this is running at the lowest I2C speed, but that's perfectly fine. It's not super fast. We end up reading 10 bytes in, about just over a millisecond, 1.3 milliseconds. That might be too slow for some applications, so you can either increase the speed if the device supports it, or you might need to choose a different serial bus. This is just an example. So whenever you're working with I2C, having a logic analyzer and having software like this makes it really easy to visualize what's going on the bus, and it makes it really easy to make changes. And you can see the changes that you've made being reflected in whatever is being sampled on the bus by the logic analyzer. So let's go back over to the slides and finish up our presentation. All right, so we took a look at PulseView. Now let's sort of summarize everything that we've gone over. I2C transactions are made up of sequences of events on the bus. Start condition is how we start everything, followed by the address of the device that we want to talk to, and its read or write bit, depending on what kind of transaction it is. Then we send the data to be read or written, depending on what direction it is. There's an acknowledge or not acknowledge for each byte, sent by whichever side is currently listening. And at the end, we have a stop condition, or a repeated start in some cases. Bus arbitration is automatic and non-destructive because of the fact that we use pull-up resistors. That takes care of bus arbitration for us, essentially, as long as every device always looks at the bus after it's changed it to make sure that it's in the state that it expects it to be. And if it's not in the state that it expects it to be, it has to stop and wait for a stop condition to appear on the bus before it can try communicating again. Most of the time, if you're not doing serious embedded device work where you have multiple controllers on the same bus and tons of peripherals, you're very rarely going to have to deal with bus arbitration. In the majority of systems, it's going to be a single microcontroller talking to a variety of sensors or memories or something. But again, it's good to understand how it works. And this same benefit from pull-up resistors is apparent in the acknowledge not acknowledge. By default, a not acknowledge will always be sent. The chip actually has to intervene, pull the bus low to say that it is acknowledging, which is important because that makes it sort of by default error proof. If something goes wrong, you're always going to get a not acknowledged back. You don't have to worry about accidentally getting something on the bus that you don't expect, because the idle state is forced by those pull-up resistors, which can't do anything but pull the bus high. There's no active device that pulls it high, which is really interesting. So either device can be talking or listening. As we said, either side might be sending data, but the controller is always in control of the clock line. So as we just saw in PulseView, even when we were reading bytes from the EEPROM, the controller was actually the one still generating those clock pulses. And then it was just allowing the peripheral to change the state of the data line. And then at the end of each byte, it would send an acknowledge saying, yes, we want more data from you. Only the controller can start and end transactions. Again, the peripherals can't do anything unless they see a start and then their valid address on the bus, followed by whatever happens, and then a stop condition or a repeated start in some cases. That's it for this presentation. I went over things, tried to squeeze it into an hour here, a little under an hour. The first question and answer session is going to be tomorrow night, Thursday, and it's going to cover any questions you have. We're going to be doing a live session. So if you have any questions, go back through the presentation, write down any questions you have or anything you missed, and I'll be more than happy to answer any questions you have. If you want, we can take a look again at that example transaction. We can look at it more in depth. If you have any questions later, after this course is complete, you can always email me at the email address at the first slide. I can't promise that I'm going to be able to give everyone a full, detailed answer, but I'll always be able to point you in the right direction. And speaking of which, there's a book that if you're interested in learning more about the I2C bus, we're going to look at it again next week. There's a bus called Mastering the I2C Bus by an amazing electronics engineer named Vincent Hempy. If you're interested in buying that book, it's available online. It's no longer in print, so it's a little bit pricey, but it is the textbook on I2C. So I highly recommend that. And next week we'll be going into software examples. So hopefully if you want to follow along with those examples, you'll have your MSP430 Launchpad. We're going to be going over some example MSP430 code, looking at how you actually use an I2C peripheral to send I2C block inside a microcontroller to communicate with peripherals and actually do something with it, which is the whole point of learning I2C. I'm going to put a link to the slides so you can download them on the project page for this course. So if you want to go back through the slides and take a closer look at anything, you're more than welcome to do that. The same thing will be true with the software. It'll be posted into a GitLab repository where anyone can take a look at the code. And we'll be going over that in detail next week. So thank you so much for watching.